Hi, this is the second lecture of the optional course on advanced nonlinear physics. Let us proceed. So remember, we aim at solving this nonlinear advection equation, rho t plus c of rho sub x equals 0. And by solving, we mean determine rho as a function of x and t for a given rho naught, initial rho naught of x, initial distribution. Let's first consider the simple case where c of rho is a constant, c naught. So we know that for this simplified equation, we lost all the nonlinear character, and the solution is simply rho naught of x minus c naught t. Okay, of course, you take that, you plug it into 1, where c of rho equals c naught, and of course, this is the solution. It means that a graphical way to construct the solution can be illustrated like that. So let's plot in the xt plane, okay? The initial distribution should be represented in the third axis. Schematically, I just draw a swarm of points there, initial points, okay? And they are parallel transported along straight line of typical equation x equals c naught t plus initial value of x. That's denoted by x bar. So it means in this plane, these straight lines have all the same slope, which is 1 over c naught. It's 1 over c naught, the slope, because t is not the abscissa, but the ordinate. Okay, so this distribution here is moved as a function of time like that. And this is the distribution at t. And one may write rho of x of t is rho naught of x bar, where for a given x and t, x bar is defined like that. Of course, x bar is x minus c naught t. That's it. Now, let's go to the more interesting case where c of rho is not a constant. There is a trick, and this trick is really what one calls the method of characteristics. Define the function psi of t, which is rho of x of t and t, where x of t is not yet specified. It's unknown at this point. So the derivative of psi with respect to t is, of course, rho sub t plus dx dt rho sub x. Now, if one chooses x of t such that dx dt equals c of psi, then of course this is identical to equation 1, to the equation we are studying, because psi is rho. So, so this will be 0, and d psi dt will be 0. This means psi is conserved along the curve x of t. And this curve, which is defined by this equation, is called a characteristic. Okay, psi being a constant, dx dt, which is c of psi, is also a constant along the characteristic. And this means the characteristic is just a straight line. Dx dt equals constant, it's a straight line. Just note here that this is not a generic feature. Compare exercise in the first tutorial. So in the case at hand, the characteristics are straight lines. And at variance with the example, the previous example of a constant c naught, here, there is a misprint, the characteristic slopes are not all the same because they are c of psi. And psi is initially, for instance, rho naught of x bar. Okay, so they are not all the same. So again, one draws here in the xt plane an initial distribution, and here one has a straight line, which is the characteristic of equation x equals an initial x bar. So here I took x bar equals 0, but might be different, plus the slope, which is c. I can evaluate the argument there, which is psi at t equals 0, since it's a constant, and it's rho naught of x bar times t. So this is the characteristic. And they don't have the same slope because rho naught of is not, a priori, is not uniform. So in the case we consider here, for instance, rho naught is more here, and C of rho naught is larger here, and so the C's are different. And sometimes the characteristics tend to shrink to get closer, or on the opposite, they get more separated. And when they get closer, the density increases, of course. And again, one has rho of xt is rho naught of x bar. So the way how to solve it is the following in practice. So one has rho of xt is rho naught of x bar, where x bar is defined by this is the antecedent. How you say that in well, it's a previous one. Well, x equal x bar plus c of rho naught of x bar t. So you solve for a given x of and t, you determine x bar here, and then you get rho of xt by this formula. Let me give another more numerical way of solving it, and take, for instance, the example of a simple nonlinear advection equation, which is Hopf equation, where C of rho is equal to rho. So the equation is rho sub t plus rho sub x equals 0. And take an initial Gaussian distribution, rho naught exponential minus x squared. So then, instead of solving this, one can numerically implement the solution very easily. Just define the an initial array with x of I and rho naught and rho of I given by rho naught. Okay. Then at time t, you take the same rho, but x changes. X is the initial one plus c of rho naught, which in our case is simply rho naught, times t. And that's it. And then you plot this new xt, this rho as a function of this new xt. And this is what is done here in this plot. So at time t equals 0, one has the Gaussian in black. Time t equals 0.5, it's in red. It has moved to the right. At time 1 it's green, 1.5, and so on and so forth, and time 3, that the purple curve there. So one observes that the solution gets multi-valued. One speaks of wave breaking. At time, it's difficult to say from this picture, but slightly larger than 1. At time t equals 1, it seems to be still okay, and in blue it's 1.5. I mean, it's multi-valued. So wave breaking in French is a déferlement. And so if the solution is multi-valued, one can invoke a simple explanation for that within the method of characteristic. Is when two characteristics cross, I don't know which precursor, which x bar I should take. I have several choices, and that's the reason why the solution gets multi-valued. So let's do some math and determine at which time wave breaking occurs. So remember, the method of characteristics is to solve amounts to determine x bar by x equals x bar plus where instead of C of rho naught of x bar, I simply note f of x bar. Okay, x equals x bar plus f of x bar t. It's just the same, oops, sorry, the same equation than here. Okay. Now, two neighboring characteristics, starting one at x bar and the other one at x bar plus dx bar, cross when I have x equals x bar plus f of x bar t, but is also equal to x bar plus dx bar plus f of x bar plus dx bar times t. And if one does first order Taylor expansion of this term, and one makes the difference of these two guys, x bar cancels, dx bar factorizes out because this is f of x bar t, which cancels, plus dx bar f prime. And this equation reads 0 equals 1 plus f prime of x bar t. Okay, and whenever t fulfills this equation, one has two characteristics cross. And the wave breaking time is the time at which wave breaking occurs first. And this is the minimum of all these solutions. It's the wave breaking time, and it's 1 over the max of minus f prime. Okay, so for instance, in the above equation of Hopf equation, remember we had Hopf equation and this initial distribution, minus f prime, which is its maximum at 1 over square root of 2, and its maximum is square root of 2 divided by e. Hence, the wave breaking time is square root of e divided by 2, which is 1.17. Slightly larger than 1, as we had seen. Okay, so this is the time after which we can no longer trust the method of characteristic. Okay, but before this time should work. And in the following, we will consider a simplified type of initial condition, not something as, well, this is simple, but something even simpler than that, simply a discontinuous initial condition. Rho naught is a constant rho2 for x larger than 0, and rho1 for x lower than 0. It means the f of x, which is here, is C2, C of rho2 for positive x, and C1, which is C of rho1 for negative x. And we'll see this point. Okay, so first, we simplify the problem. Define U equals C of rho. Okay, and it's very easy from equation 1, which I will call, which is this one, to show actually that U verifies Hopf equation, ut plus ux equals 0. And just need to solve Hopf equation. And once this is done, you obtain rho by inverting this. It means rho is C minus 1 of U. So might not always be possible to invert if C is non-monotonous, but let's assume that C is monotonous. And there are interesting cases where it's not. Okay, for simplification, we will not discuss them at this point. So let's consider the Riemann type of initial condition. This type of initial condition is called Riemann. It's no longer rho, it's U, okay, U1 and U2. So initial U naught of x, which is the initial distribution, is simply a step function where U1 is smaller than U2, okay? And we'll see that the solution corresponds to what is called a rarefaction wave. So let's draw the characteristics. So for positive x, the characteristics have slope 1 over u2, okay? And the limiting case is the one that starts at 0 and is x equals u2t. For negative x, the characteristics have the slope 1 over u1, all parallel, and the limiting case is this thick blue line, x equals u1t. So one has obtained all the characteristics in this region, but in the dashed triangle there, one has no characteristics. It means one cannot find an X bar from which a characteristic would be issued and would reach this gray area. So that's a problem for the method. Actually, this problem just comes from the fact that the initial distribution is too schematic. And one should, instead of taking a step function, one should smooth it. And then it's very simple to see that one will have a straight line of this type in this gray region. You can see it this way. Well, you fill the green region by smoothing, as I said, the initial distribution. Remember that one has, in our case, x equals x bar plus u naught of x bar t. Where now, around 0, u naught interpolates smoothly from u1 to u2. But x bar is always almost 0. Okay, it's a very steep interpolation, and u naught, which is here, interpolates from u1 to u2. So one has a characteristic of the form x equals ut, where u is in between the two limiting cases. And it means that in this red region there, u is equal to u2. And this is if x is larger than u2t, or if u2 is smaller than x over t. In this blue region there, u is u1. And this is if x is smaller than u1t. And in between, one has, from here, u is x over t. Okay? And if you draw it, you get something like that. So in green, the initial distribution, and now in red, the distribution at time t. So this was easy to obtain from the method of characteristic. This was also easy to obtain, and in this region there, u is simply x over t, as we just saw. And so this point, and the origin of our course, of course, aligned. And this type of wave here is called a rarefaction wave. Actually, it's more an increase in u, but still, that's the term which is commonly accepted. Okay. No. Now, as an exercise, use this method to describe what happens after a traffic light turns green. So consider, okay, so we consider the traffic flow problem, and the initial distribution of cars is the following: constant and at jam density here. I have cars are bumper to bumper here, and at x equals 0, I have the traffic light, which is initially red, and no car ahead. And the traffic light has been red for a while, so this goes to minus infinity. Okay? Now remember, for the traffic flow problem, the shape of C of rho. Oops. It's like that, C of rho, as a function of rho. This was done in the previous lecture. it starts at a given value I denote C naught, then gets decreases, always decreasing, cancels at rho equals rho m, and at the jam density, it has a value I denote by Cj, which is negative. Okay. Now, well, let's draw the characteristics. It's very easy. For negative x, they go backwards at velocity Cj, so the slope is 1 over Cj. For positive x, they go in the positive x direction at velocity C naught, because I have 0 density here. And the slope is 1 over C naught. And in between, I interpolate as usual. So rho of x now, well, in this region there for a given t, in the green, I have a constant rho j. Okay, then my first car here, which was at 0 density, moves along this characteristic there with slope with velocity C naught, and it is at C naught t. Ahead, I have 0 density. All these characteristics here correspond to 0 density. And in between, I mean, of course, for instance, this guy, the density distribution there has moved backwards at velocity Cj. Here, it has moved in the positive x direction at velocity C naught. For instance, here at rho m, it hasn't moved. And this red line here is simply the inverse function of x over t. Okay? And at rho m, it doesn't move. And indeed, this is what happens when you wait at the traffic light. If you're here, for instance, you see that the first cars, they start moving before you do. You need to wait a certain time until you reached by the modification of density. So this was this small exercise of traffic flow. Now, let's go back to the Riemann problem for the Hopf equation, remember? And we take now a situation where U naught is larger than U2, okay? Previously, it was the opposite. Let's show the characteristics. So here, the slopes are 1 over U1. U1 is large, a small slope. And here the slope are, in the blue region, 1 over U2. U2 is small, large slope. And these are the two limiting cases. This point here moves along these characteristics. Tick x equals U2t. And this point here moves along this thick red characteristic, x equals U1t. And now I have an issue there, some characteristic cross. Well, this occurs. I'm aware of this potential problem. The point is that here, the wave-waving time is 0 because characteristic cross even at t equals 0. Well, never mind. Let's try to follow our strategy and to see what's the shape of the solution of u of x and t. Well, I get something like that, okay? This guy has moved right with velocity u1. Okay, so here I made a mistake. It's u1 t because u1 is larger. So that's this line. This guy here has moved right with velocity u2. sorry, it's a mistake, it's U2 here. And if one considers also this part, one will have in this region, as previously, U equals x of t. So actually, I find a solution which is multi-valued, and since I have a schematic initial condition, I have a schematic multi-valued solution which makes a zigzag like that. Okay, and that's not acceptable. So how to solve? Well, what one could just put the blame on the method of characteristics and say one cannot apply it here. Still, I mean, it's a very neat method, so we like it. Let's try to save part of it. For instance, in this region there, it's clear that it works until this point here, which is U2t. And there also ahead, it clearly works until this point, which is U1t. So it's only, the problem is only in between. Why not try to cut here to have a discontinuous jump to the lower branch? So the idea would be, since the multi-valued solution is not acceptable, replace the multi-valued solution by something which is part of the solution, has a discontinuity, and then again part of the solution. So how could one fix the position of this discontinuity? And the solution is to use current conservation. Okay, one point is, I will enforce a discontinuous solution, although my initial distribution might be continuous and smooth, like here the exponential. Okay, the discontinuity is really triggered by wave breaking. It's not issued by the fact that, for instance, here I have an initial discontinuous function. Even if my initial function is continuous, I'm claiming that I will try to find a discontinuous solution. And the way how to do that is to impose current conservation, which amount to say that I make a cut at a point S, which is called a shock point. And this type of solution is called a dissipative shock wave. So I fix the point S such that the area of these blue regions are the same. And by what do I mean? Well, let's take a segment between point x1 and x2. These points are fixed, okay? And let's try to compute the velocity of the shock. And one does that by enforcing the conservation of the number of particles between x1 and x2. So remember, the time derivative of the number of particles between x1 and x2 is what gets in at x1, which is the incoming flux, and what gets out at x2, outgoing flux. This is this quantity. We saw that in the previous lecture. Now, I want to use a discontinuous function. So it's better here in this integral to point by s and to write d dt of the integral between x1 and s of rho, which is this there, plus the integral between s and x2 of rho, which is now the lower branch here, equals q of x1 minus q of x2. So let's derive that. One has first the derivation that comes from this point, and that gives rho at s times s dot. But rho at s it's rho minus or rho at S minus is at this point here. Okay. Then also one has a derivative from this contribution. And that's simply rho at S plus, now here, times the time derivative of S, which I denote by S dot. And one has also, when one does the sum and when deriving, which is the derivation, the partial derivative with respect to t between x1 and x2, dx equals 2x1 minus q of x2. And now let x1 go to s, still remaining always lower than s, and x2 go to s, still remaining larger than s. Okay? And very simply, one obtains, I let you do the math, but S dot equals Q plus, because X2 goes there, and that will be just Q of S plus, okay, just above S. One obtains Q plus minus Q minus divided by rho plus minus rho minus. It's a very simple computation to go from there to there. And this defines the velocity of the shock. And this guy might be time dependent because Q plus or minus a priori depend on time, and also this quantity here, which I denote by rho minus, and this one by rho plus, a priori depend on time. If you do that for the previous schematic problem, you find that S dot is just, do it as an exercise, U1 plus U2 divided by 2. So I'm just here in the middle, and indeed, these two areas then will be the area of this triangle there, from U1 to U1 plus U2 divided by 2 times T. And this other area here will be the same. So this is the end of this lecture. Just for the next one, I ask you to work on the tutorials. The first part of the tutorials is a set of simple exercises on the method of characteristics. Then there is another exercise, which is a simple generalization of this solution there, or no, of this problem there. One takes 2 steps. And then it's a more involved discussion of some aspects of traffic flow. And this is the end of this lecture.